Before space existed, there was no where. Before time existed, there was no when. And yet, something was there. Something that left fingerprints on the birth of the universe. Something so strange that even the laws of physics collapse when we try to describe it. Because the real mystery isn't what came after the Big Bang. The real mystery is, how can anything exist when the stage of existence itself didn't exist yet? Tonight, we're going to step into that impossible moment. The moment before even existed. And what you're about to learn will challenge every instinct your brain uses to understand reality. Imagine you're watching a movie and someone asks you what happened before the first frame. Nothing happened. There is no before the first frame. The movie begins when it begins. But here's where it gets strange. At least with a movie, there's a projector, a film reel, a world outside the movie where time continues. With the universe, there's nothing outside. The universe isn't a thing in space and time. The universe is space and time. So when we talk about the Big Bang, we're talking about the moment when the movie projector itself turned on, when the very concept of frames came into existence. You might think I'm being evasive, that I'm dodging the question. You want to know what was there before the Big Bang. Your intuition screams that there must have been something. After all, how can something come from nothing? That's not how the world works, right? Every effect has a cause. Every beginning has something that came before it. But what if your intuition is wrong? What if it's not just slightly wrong, but catastrophically, fundamentally wrong about the deepest nature of reality? Consider this. When you ask what came before the Big Bang, you're assuming that the universe is like every other thing you've encountered in your life. You were born, so there was a time before you existed. This building was constructed, so there was a time before it stood here. The Earth formed from a disk of debris around the young sun, so there was a time before Earth existed. You're extrapolating from every single experience you've ever had and applying it to the universe itself. But the universe isn't a thing in the world. It is the world. It's not an object among other objects. It's the totality of everything that exists, and that totality might operate by completely different rules than any individual thing within it. Here's something that will twist your mind. Physicists don't agree on whether the question is even answerable. Not because we lack data, though we do, but because they fundamentally disagree on whether the question makes sense. Some of the greatest minds in physics will tell you that asking what came before the Big Bang is a category error, like asking what the color of jealousy smells like. The question smuggles in assumptions that don't apply. It treats time as if it's a river that's always been flowing, when in fact time might be more like water vapor that condensed into liquid at a specific temperature. Other physicists will tell you that of course there was something before, that the Big Bang might not be the beginning at all, but just a transition point, a phase change in something much older and much stranger. Let me paint you a picture that might help, though every analogy eventually breaks down when dealing with the beginning of everything. Imagine you're an ant living on the surface of a balloon. Your entire universe is the two-dimensional surface of this balloon. You can walk north, south, east, west, but you have no concept of up or down. Those directions don't exist in your world. Now someone starts inflating the balloon. From your perspective, space itself is expanding. The distance between you and your fellow ants is growing, but not because you're moving through space. Space itself is expanding. There's more surface on the balloon than there used to be. Now let's run this in reverse. Deflate the balloon. The surface shrinks. Keep going. Smaller and smaller. Eventually, you reach a point where the balloon has zero size, a single point. That's your Big Bang. But here's the crucial part. You can't ask what's inside the balloon, because inside is a direction that doesn't exist in your universe. You literally cannot point to inside. It's not that there's nothing there, it's that there is not a there. The word there doesn't apply. For us, trapped in our three-dimensional space as it expands through time, the Big Bang is similar. Wind the clock backward and space shrinks. 13.8 billion years ago, all of space, not all the stuff in space, but space itself, was compressed into something unimaginably tiny. Not a tiny thing in a larger space, but all of space was tiny. And if you ask what was outside that tiny space, the answer isn't nothing. The answer is that outside doesn't exist. There is no outside. The question is malformed. But your brain rebels against this. Of course there's an outside. Of course there was a before. How can there not be? This is where human intuition becomes not just unhelpful, but actively misleading. Your brain evolved to model medium-sized objects moving at medium speeds in a world of human-scale physics. You developed intuitions about how things work based on throwing rocks, walking across savannas, tracking animals, understanding social relationships. None of that prepared you for the physics of the very small, the very fast, the very massive, or the very early. At those extremes, reality stops behaving like anything you've experienced. Particles exist in multiple places simultaneously. Time dilates and contracts. Cause and effect become fuzzy. And at the absolute extreme, the beginning of space and time itself, your everyday intuitions aren't just wrong. They're not even wrong. They're incoherent. Think about the surface of Earth. If you start at the equator and walk north, you're moving toward the North Pole. Keep walking, and eventually you reach it. Now, standing at the North Pole, someone asks you, "What's north of here?" There's no answer. It's not that there's a secret place further north. It's not that you're forbidden from going there. It's that the question assumes a direction, north, that stops having meaning at that point. Every direction from the North Pole is south. The concept of north breaks down. This is exactly what happens when you ask what came before the Big Bang. The concept of before breaks down. Time itself reaches a boundary, and beyond that boundary, or rather, not beyond, because beyond is a temporal concept, there simply isn't a when to point to. Stephen Hawking put it this way: asking what came before the Big Bang is like asking what's south of the South Pole. The question contains its own answer. There is no south of the South Pole. There is no before the Big Bang. Time itself began at that moment. But does that really satisfy you? It shouldn't. Because even if time began then, even if the question is technically meaningless, there's still something deeply unsettling about the idea that time just starts, that there's a first moment with nothing before it. It feels incomplete, unfinished, like we're missing something fundamental. And maybe we are. Maybe the problem isn't with the universe, but with our understanding of time. We treat time like an absolute background against which events unfold, a universal clock ticking away regardless of what's happening in the universe. But Einstein shattered that notion over a century ago. Time isn't absolute. It's relative. It's woven together with space into a single fabric called spacetime. This fabric can stretch, compress, warp, and bend. Near a massive object, time runs slower. Move faster through space, and you move slower through time. Time isn't a river flowing at a constant rate. It's more like molasses, thick in some places, thin in others. Its flow dependent on the local conditions of mass and velocity. So when we wind the clock back to the Big Bang, we're not just going back to the beginning of time. We're going back to a point where time itself becomes so warped, so compressed, so fundamentally different from what we experience, that our normal understanding of it completely breaks down. At that point, talking about before is like trying to use a map of New York to navigate Tokyo. You're using the wrong conceptual framework entirely. But let me introduce another possibility, one that's going to make your head spin even more than what I've already told you. What if there was something before the Big Bang, but it wasn't another universe or another space? What if it was a completely different kind of reality altogether? What if the Big Bang wasn't the beginning of everything, but just the beginning of this particular configuration of reality, this particular crystallization of spacetime? Some of the most cutting-edge theories in physics suggest exactly that. They propose that the Big Bang was a transition point, a phase change, like water turning to ice. Before the transition, there was something, not space as we know it, not time as we experience it, but something more fundamental from which both emerge. These theories go by different names: eternal inflation, the multiverse, quantum cosmology, pre-Big Bang scenarios, but they all share a common thread. The Big Bang might not be the ultimate beginning. It might just be a really important moment in a much longer, much stranger story. Consider eternal inflation. This theory suggests that our universe, the region of space that began with our Big Bang, is just one bubble in an infinitely larger, eternally inflating superstructure. Imagine a pot of boiling water, with bubbles constantly forming and growing. Each bubble is a universe with its own Big Bang, its own laws of physics, its own history. The water itself, the inflating superstructure, has no beginning and no end. It's eternal. It's always been inflating, always spawning new bubble universes, each one born from what looks like a big bang from the inside, but is really just a phase transition in this larger eternal process. From inside our bubble, we see the Big Bang as the beginning of everything because we can't see outside the bubble. The walls of the bubble, the edge of our observable universe, are moving away from us faster than light can travel, creating a kind of cosmic horizon beyond which we cannot see. We're trapped inside our bubble universe, and from our perspective, its birth is the only beginning that matters. But zoom out, look at the larger structure, and you'd see that our Big Bang is just one of countless similar events happening all the time, everywhere, throughout an infinite expanse that never began and will never end. But wait, if eternal inflation is correct, if there's this eternal inflating superstructure that's always existed, doesn't that just push the question back? Now, instead of asking what came before the Big Bang, we're asking what came before eternal inflation. Where did the inflating structure come from? You see the problem. Every answer just generates a new question. Every solution just pushes the mystery back one level. It's turtles all the way down, except instead of turtles, it's universes or quantum fields or mathematical structures, or something even more abstract that we don't have words for yet. Unless there's a way to avoid the infinite regress. Unless there's a scenario where the universe, or the multiverse, or the quantum field, or whatever you want to call ultimate reality, doesn't need a beginning because it exists in a way that transcends the usual rules of causation. This is where physics starts to blend into philosophy, where the equations give way to pure conceptual thinking about the nature of existence itself. Some physicists and philosophers propose that the universe might exist necessarily, not contingently, not as the result of some prior cause, but as a brute fact, something that simply must exist by its own nature, like how a triangle must have three sides. This is a radical idea. Everything in your experience is contingent. You exist because your parents existed. Your parents existed because their parents existed. This planet exists because a cloud of gas collapsed. That gas cloud existed because of earlier processes in the galaxy's history. Everything you've ever encountered exists because something else caused it to exist. But what if ultimate reality, whatever that is, doesn't work that way? What if it just exists, period, without needing a cause, without needing something before it? This sounds like a cop-out. It sounds like we're just giving up, throwing our hands in the air and saying, it's magic. But it might actually be the only logically coherent answer. Because consider the alternative. If everything needs a cause, then you have an infinite chain of causes stretching back forever. Cause A caused event B, which was itself caused by cause C, which was caused by cause D, and so on infinitely. But an infinite regress of causes is problematic. Philosophers have debated this for millennia. If you have an infinite chain of causes with no first cause, then in a sense, nothing is truly explained. Each link in the chain is explained by the previous link, but the chain as a whole has no explanation. It just exists as an infinite sequence with no foundation. The alternative is that somewhere, somehow, there has to be a first cause, something that exists without being caused by anything else, something that stops the regress. And that something would have to be very strange indeed. It would have to be self-existent, necessary, uncaused. It would have to be the kind of thing that doesn't require anything before it or outside it to explain why it exists. And that might be what the universe is at its deepest level. Not the universe as you experience it, stars and galaxies and space expanding from the Big Bang, but the fundamental reality underlying all of that. The quantum vacuum, or the mathematical structure, or the laws of physics themselves, or something even more abstract that generates all of those things. Here's where it gets truly weird. Some physicists argue that the universe might have created itself, not through some mystical process, but through the bizarre logic of quantum mechanics. In quantum mechanics, particles can pop in and out of existence without cause. This isn't speculation. We observe it happening in laboratories. Particles and antiparticles appear spontaneously in empty space, exist for a fraction of a second, then annihilate each other and disappear. It's called quantum fluctuation, and it's a real, measured phenomenon. The vacuum of space isn't actually empty. It's seething with these temporary particles, this quantum foam of existence flickering in and out of being. Now scale that up. Way up. If a particle can appear from nothing through quantum fluctuation, why not an entire universe? The laws of quantum mechanics don't prohibit it. In fact, they might require it. Given enough time, or rather, given a quantum state that exists outside of time, a universe-sized fluctuation could occur. The entire universe, with all its matter and energy and space-time, could be one enormous quantum fluctuation that happened to last long enough to evolve into everything we see around us. But there's a catch. Actually, there are several catches. First, for a quantum fluctuation to occur, there needs to be a quantum field, the underlying substrate from which the fluctuation emerges. So we haven't eliminated the need for something pre-existing. We've just changed what that something is. Instead of asking what came before the Big Bang, we're asking where the quantum field came from. Second, quantum fluctuations in a vacuum have an energy cost. They typically appear in particle-antiparticle pairs that quickly annihilate because the universe borrows the energy to create them from the quantum field, then pays it back when they disappear. For a universe-sized fluctuation, the energy cost would be enormous. Where does that energy come from? This is where another mind-bending idea comes in. The total energy of the universe might be zero. Positive energy exists in the form of matter and radiation, all the stuff you can see and touch and measure. But negative energy exists too, in the form of gravity. Gravity is an attractive force, and in the mathematics of general relativity, gravitational potential energy is negative. When you add up all the positive energy of matter and radiation and all the negative energy of gravity, they might exactly cancel out. The total energy of the universe might be precisely zero. If that's true, then the universe isn't borrowing energy to exist. It's not violating conservation of energy. It's a zero-sum game. The universe can fluctuate into existence because it costs nothing to create it. The positive energy of everything in it is perfectly balanced by the negative energy of gravity holding it all together. The universe is literally a free lunch, the ultimate example of getting something from nothing because the something and the nothing add up to the same thing. But let's pause and appreciate how strange this is. We started with the question, what was before space? And we've arrived at a scenario where the universe might be a quantum fluctuation in a pre-existing quantum field, where the total energy is zero so it doesn't violate conservation laws, where time itself begins at the Big Bang, so the concept of before doesn't apply, and where the whole thing might be one bubble in an eternally inflating multiverse that never began. Each explanation opens up new questions. Each answer reveals deeper mysteries. You might be feeling frustrated at this point. You wanted a clear answer. You wanted me to tell you what was before space. But I've given you paradoxes, contradictions, competing theories, and more questions than answers. That's not me being evasive. That's the actual state of human knowledge about this question. We're at the frontier of what's knowable, perhaps beyond it. We're using tools, physics, mathematics, logic, that were developed to understand the universe as it exists now, and we're trying to extrapolate them backward to a regime where those tools might not even apply. Imagine you're an ant trying to understand human consciousness. You can observe humans moving around, communicating, building things. You can see the effects of consciousness, but the thing itself, the subjective experience of what it's like to be human, is completely inaccessible to you. You lack the cognitive architecture to even form the right concepts. You're trying to solve a problem with tools that are fundamentally inadequate for the task. That might be our situation with the question of what came before the Big Bang. We might be ants trying to understand consciousness, using three-dimensional spatial intuition and linear temporal reasoning to probe a question that requires conceptual frameworks we haven't invented yet. But let's not give up. Let's push further. Because there's another approach to this question, one that's even more radical than anything I've mentioned so far. What if the question, what came before the Big Bang, is not just difficult to answer or currently unanswerable, but actually meaningless? What if time itself is an illusion? This sounds insane. Time is the most real thing there is, right? You age. You remember the past, but not the future. Cause precedes effect. How can time be an illusion? But some of the deepest theories in physics suggest exactly that. They suggest that time as you experience it, as a flowing river carrying you from past to future, is not fundamental to reality. It's emergent, something that appears at our scale but disappears when you look closely enough at the underlying structure of reality. Einstein showed us that time is relative, that it flows at different rates depending on your motion and the gravitational field you're in. That was radical enough. But some modern approaches to quantum gravity go further. They suggest that at the most fundamental level, the level of quantum geometry or the quantum structure of spacetime itself, time doesn't exist at all. There is no flow, no change, no becoming. There just is a timeless mathematical structure that exists all at once, and the flow of time you experience is an artifact of your perspective, a result of the way information is organized in your brain and memory. Think of it like a film reel. The film contains all the frames of the movie, all existing simultaneously as patterns on celluloid. None of the frames is more real or more present than any other. They all just exist. But when you play the film through a projector, you experience them in sequence. You experience a flow from one frame to the next. The characters in the movie seem to move and change and live through time. But that flow isn't in the film itself. It's in the way the film is being processed and presented. The flow is in the playing, not in the thing being played. Maybe the universe is like that film reel. Maybe all moments, past, present, future, the Big Bang, the heat death of the universe, every moment of your life, all exist simultaneously as different regions of a timeless mathematical structure. The flow of time you experience is just the way you're processing that structure, the way your consciousness moves through it, or the way information is organized in your memory. From outside that structure, from a God's eye view, though using that term makes me uncomfortable, there is no before or after. There is no flow. There is just the complete four-dimensional structure of the universe existing as a timeless whole. If this is true, then asking what came before the Big Bang is like asking what frame comes before the first frame of a film. From inside the film, the first frame is the beginning. Time starts there. But from outside, looking at the film reel, you can see that it's just one end of a physical object. There are reasons the film is the length it is, reasons it starts where it starts, but those reasons exist in a different conceptual space than the space of the film itself. Similarly, there might be reasons the universe has the structure it does, reasons it extends from the Big Bang to whatever its endpoint is, but those reasons exist in a different conceptual space, a space of mathematical necessity, or quantum probabilities, or something else entirely. This is called the block universe view, or eternalism. It's the idea that past, present, and future all exist equally, that the flow of time is an illusion generated by consciousness or by the thermodynamic arrow of entropy. It's a view that many physicists take seriously, though it's deeply counterintuitive and raises enormous philosophical problems about free will and the nature of consciousness. But it offers a potential resolution to the question of what came before the Big Bang. Nothing came before it in time, because time itself is just a dimension of this larger timeless structure, and asking what came before is asking the wrong kind of question. But even this doesn't fully satisfy, does it? Because even if time is an illusion, even if the block universe exists as a timeless whole, we still want to know why this particular block universe exists. Why this structure and not some other one? Why does anything exist at all rather than nothing? We've moved the question from the temporal realm to the ontological realm, from asking about temporal priority to asking about existential grounding. That might actually be progress, a more refined version of the question that gets closer to what we really want to know. Let me take you even deeper. There's a view in physics and mathematics that the most fundamental description of reality isn't physical at all, but mathematical. Not that there's a mathematical description of physical reality, but that mathematical structure is the reality, and what we call physical stuff is just our way of experiencing certain aspects of that mathematical structure. This is sometimes called mathematical Platonism or the mathematical universe hypothesis, championed by physicist Max Tegmark and others. Here's the idea. Mathematics isn't something we invented to describe the universe. Mathematics is what the universe is. When you look at an electron, you're not looking at a tiny ball of stuff that happens to behave according to mathematical laws. You're looking at a mathematical structure, a quantum field configuration an excitation in the electron field that your brain interprets as a particle. The equations aren't describing reality. They are reality. Everything that physically exists is just an aspect of mathematical existence. If this is true, and it's a big if, then asking what came before the Big Bang might be like asking what comes before the number 1. Numbers don't have temporal priority. They just exist in the timeless realm of mathematical truth. The number 7 doesn't come after the number 6 in time. It comes after it in logical sequence, in the abstract ordering of the number line, but both exist eternally in the mathematical realm. Similarly, the Big Bang might not have temporal priority in the way you think. It might just be a boundary condition of the mathematical structure that describes our universe, like how the number 1 is the boundary of the positive integers. This sounds incredibly abstract, and it is. But it's also potentially the most fundamental answer we can give. If reality is ultimately mathematical, then asking what came before it is a category error. Mathematical truths don't have temporal origins. The Pythagorean theorem didn't come into existence at some point. It's timelessly true, or rather, it exists outside of time altogether in the realm of abstract truth. If our universe is a mathematical structure, then it exists in the same way, not in time, but as a timeless mathematical truth. The Big Bang isn't an event that happened at a time. It's a boundary condition in the mathematical structure, the edge of the space-time manifold, the point where the equations break down or transition into a different regime. But this raises yet another question. Why does this particular mathematical structure exist and not others? Or do all possible mathematical structures exist equally? Each one is real as any other, and we just happen to find ourselves in this one because it's one of the few structures capable of supporting observers like us? This is the idea of the mathematical multiverse, that every mathematically consistent structure exists, and our universe is just one of infinitely many such structures, each with its own laws of physics, its own history, its own geometry. In this view, there's no cosmic selection process that chose our universe over others. All possible universes exist. We're in this one simply because we couldn't exist in most of the others. The universes that don't have the right physical laws to support stable atoms, or chemistry, or evolution, or consciousness. Those universes exist too, but they're empty of observers. We find ourselves in a universe compatible with our existence not because it was designed for us, but because we couldn't exist in the ones that weren't compatible. It's the anthropic principle taken to its logical extreme. This is either deeply satisfying or deeply unsatisfying, depending on your philosophical temperament. On one hand, it explains why our universe has the particular laws and constants it does, because all possible sets of laws exist somewhere, and we're naturally in one that allows us to exist. On the other hand, it feels like giving up on explanation. It's saying the universe is the way it is because it could be many ways, and we're in one of those ways. It doesn't tell us why mathematical structures exist in the first place, or why the particular structure we're in has the features it does beyond the fact that we can observe it. Let me circle back to something I mentioned earlier but didn't fully explore, the idea that the universe might have no beginning at all, not because it's eternal in the way we usually think of eternity, but because the question of beginning only makes sense within time, and time itself might be circular or closed or infinite in ways that make the concept of a first moment incoherent. Some cosmological models propose exactly this. The cyclic or oscillating universe model suggests that the Big Bang wasn't a beginning but a bounce, a point where a previous contracting universe reached maximum density and rebounded into expansion. Before our Big Bang was a big crunch of a previous universe. That universe had its own big crunch before it, and so on infinitely into the past. Each cycle might be identical to the others, an eternal recurrence where the same universe is born, evolves, dies, and is reborn over and over. Or each cycle might be slightly different, with different physical constants or different initial conditions, creating an infinite sequence of unique universes following one another in time. Or consider the conformal cyclic cosmology proposed by Roger Penrose. In this model, the far future of our universe, after all the stars have died, all the black holes have evaporated, and nothing remains but a thin soup of photons and other massless particles. becomes mathematically equivalent to the Big Bang of a new universe. The infinite future and the initial singularity are the same thing, connected through a conformal transformation. Time doesn't end. It wraps around. The end is the beginning, and asking what came before the Big Bang is like asking what comes before the beginning of a circle. There is no before because time is closed, forming a loop. These models are speculative. They face mathematical and observational challenges. But they represent serious attempts by serious physicists to grapple with the question of cosmic origins in ways that avoid the conceptual trap of a first moment. They suggest that the universe might be far stranger than we imagine, that the structure of time itself might be different from our intuitive linear flow from past to future. And then there's the most unsettling possibility of all, that we might never know. Not because the answer is difficult or because we need better telescopes or more advanced mathematics, but because the answer might be fundamentally inaccessible to us. We might be asking a question that transcends our cognitive capabilities, that requires forms of reasoning or intuition that humans simply don't possess and perhaps can't possess. Think about how much of modern physics is already beyond human intuition. Quantum mechanics tells us that particles exist in superposition in multiple states simultaneously until they're measured. That makes no sense to our everyday experience. General relativity tells us that mass warps the fabric of space-time, that gravity isn't a force but a curvature of geometry. That contradicts every intuition you have about how objects move and interact. String theory proposes 10 or 11 dimensions, with 6 or 7 of them curled up so tiny we can't perceive them. You can't visualize that. Nobody can. We can work with the mathematics, but true intuitive understanding is beyond us. These theories describe reality as it actually is, but we can only access them through abstract mathematics. We've lost the ability to visualize or intuitively grasp what's going on. We're navigating through symbols and equations, trusting that the math will guide us to truth even when the truth is something our brains weren't designed to comprehend. And if that's true for quantum mechanics and relativity, theories about the universe as it exists now, how much more true might it be for questions about the origin of existence itself? We might be fundamentally limited, not just technologically limited, not just temporarily limited until we invent better instruments or smarter theories, but inherently, permanently limited by the nature of human cognition. We're biological creatures with brains shaped by evolution to solve specific problems in a specific environment. Those problems were things like finding food, avoiding predators, cooperating with other humans, and reproducing. Natural selection didn't optimize us for understanding quantum gravity or the origin of spacetime. The fact that we've gotten as far as we have is remarkable, perhaps even miraculous. But there might be a ceiling, a point beyond which human intelligence simply cannot go, where the questions become too abstract, too removed from anything we can relate to experience, for us to truly grasp. This is a humbling thought. It means accepting that there are questions we might always wonder about, but never answer. The question, what came before space, might be one of them. We can propose theories, construct mathematical models, gather observational data, and refine our understanding. But we might never reach the point where we can confidently say, this is what was before the Big Bang. This is why the universe exists. The answer might be forever out of reach, not in the sense that it's hidden from us, but in the sense that we lack the cognitive architecture to even formulate the answer in a way that makes sense. Or maybe not. Maybe I'm being too pessimistic. Maybe the next generation of physicists, or the generation after that, will have an insight that cracks the problem wide open. Maybe they'll discover a new mathematical framework or a new experimental technique that reveals the answer in a way we can understand. Maybe artificial intelligence, with cognitive abilities that exceed our own, will solve the problem for us. Maybe the answer is waiting just beyond the horizon of our current knowledge, and we're closer than we think. But right now, standing here in the early 21st century, surveying everything we know about physics and cosmology and mathematics, the honest answer to what was before space is a constellation of possibilities, none of them proven, many of them deeply strange, all of them challenging our basic intuitions about existence and causation and time. Maybe time began at the Big Bang, and there is no before. just like there's nothing north of the North Pole. Maybe the Big Bang was a transition point in an eternally inflating superstructure, one bubble among infinite others. Maybe the universe is a quantum fluctuation that sprang from nothing because its total energy is zero. Maybe time itself is an illusion and the universe exists as a timeless mathematical structure. Maybe reality is fundamentally mathematical and the Big Bang is just a boundary condition in that structure. Maybe the universe goes through infinite cycles of birth, death, and rebirth. Maybe there are aspects of reality we'll never understand because our brains aren't equipped to understand them. Or maybe the answer is none of these things. Maybe it's something we haven't thought of yet, something that will seem obvious in retrospect once someone finally figures it out. The way heliocentrism seems obvious now, but was revolutionary when Copernicus proposed it. Maybe we're like people in the Middle Ages trying to understand electromagnetism or quantum mechanics. Not just wrong in our theories, but wrong in our entire conceptual framework, asking questions in a language that doesn't map onto reality correctly. What I can tell you with certainty is this. The question, what was before space, is one of the deepest and most important questions humans have ever asked. It gets at the very foundations of existence, at the nature of reality itself. And the fact that we've made progress on it at all, that we've developed theories and models and mathematical frameworks that even attempt to address it, is a testament to human curiosity and ingenuity. We're apes who climbed down from the trees and started asking questions about the origin of everything. That's astonishing when you think about it. We're not content with the surface level of reality. We dig deeper. We ask why. We demand explanations. We push against the boundaries of knowledge. And sometimes, when we push hard enough, those boundaries move. Not always in the direction we expected. Not always revealing what we hoped to find. But they move. We learn something. We refine our understanding. We discover that the universe is stranger, more subtle, more mathematically elegant than we imagined. We discover that the simple questions, where did we come from? Why is there something rather than nothing? What was before space? Don't have simple answers. They have complex, nuanced, often paradoxical answers that require us to expand our conceptual horizons, to think in new ways, to let go of intuitions that no longer serve us. So what was before space? I've given you a dozen possible answers, and the truth is that I don't know. Nobody knows. But asking the question, wrestling with it, exploring the implications of different possible answers, that's how we push forward. That's how we expand the circle of human knowledge. And even if we never find a definitive answer, even if this question remains forever at the edge of what's knowable, the journey toward understanding is itself worthwhile. Because in trying to answer it, we learn about the nature of time, the structure of space-time, the laws of quantum mechanics, the mathematics of infinity, and the limits of human cognition. We learn about ourselves and our place in the cosmos. We learn humility in the face of mysteries that might be bigger than we are. But let's not stop there. Let's push even harder. Because there's another angle to this question, one that might be even more fundamental than anything I've discussed so far. What if the very distinction between something and nothing is illusory? What if asking what came before space is based on a false dichotomy between existence and non-existence? You think you know what nothing means. It means the absence of everything. No matter, no energy, no space, no time. Complete and utter emptiness. But is that even possible? Can nothing actually exist, or is the concept of nothing itself incoherent? Philosophers have wrestled with this for thousands of years, and physicists are now joining the debate because it turns out that what we mean by nothing has profound implications for cosmology. Here's the problem. Whenever you try to imagine nothing, you're imagining something. You picture empty space, a black void, a vacuum. But empty space isn't nothing. It's space, a geometric structure with properties and dimensions. It's part of the universe, part of the fabric of reality. Even if it contains no particles, no energy, it's still something. The quantum vacuum, which seems like nothing because you can't see or touch anything there, is actually seething with activity at the quantum level. Virtual particles pop in and out of existence. Quantum fields permeate it. It has an energy density, albeit a very low one. It's very much something, not nothing. So what would true nothing be? Not empty space, because space is something. Not a quantum vacuum, because quantum fields are something. Not even the mathematical framework or the laws of physics, because those are abstract structures, and structures are something. True nothing would be the absence of all of that. No space, no time, no laws, no mathematical truths, no logical principles. Nothing at all. Not even the potential for something. But here's where it gets weird. Such a nothing might be logically impossible. Because the statement, "there is nothing," is itself a statement about reality. It's claiming that the set of existing things is empty. But to make that claim, you need the concept of a set, which is a mathematical object, which is something. You need logic to formulate the statement, and logic is a structure, which is something. The very attempt to describe or conceive of absolute nothing seems to require tools and concepts that themselves constitute something. Some philosophers argue that existence is more fundamental than non-existence. That being is more basic than non-being. That the default state isn't nothing but something, and the question isn't, why is there something rather than nothing? But rather, why would there ever be nothing? This flips the entire problem on its head. Maybe we've been approaching this backward. Maybe the puzzle isn't explaining how something came from nothing. Maybe the puzzle is that we ever thought nothing was a real possibility in the first place. If existence is more fundamental than non-existence, if something is the default and nothing is the impossibility, then there doesn't need to be a first cause or a beginning. There's just existence, manifesting in various forms, and our universe with its Big Bang is one particular manifestation. Before our universe was space, there was some other form of existence. Not nothing, but something else. Maybe a different kind of geometry. Maybe a different dimensionality. Maybe pure mathematical structure without physical instantiation. Maybe something we don't have words for because our language evolved to describe objects in three-dimensional space moving through time, and this prior form of existence doesn't fit that template. This connects back to the idea I mentioned earlier about the mathematical universe hypothesis. If mathematical structures exist necessarily, if they simply must exist by virtue of being logically consistent, then asking why there's something rather than nothing becomes absurd. There's something because mathematical structures exist, and they exist because it would be incoherent for them not to exist. You can't have a possible world where the number 2 doesn't exist, or where the Pythagorean theorem is false. These are necessary truths, truths that hold in all possible worlds, or rather, truths that define what a possible world is. And if our physical universe is one such mathematical structure, or an element of one, then it exists with the same necessity. Not contingently, as if some external cause brought it into being, but necessarily, as a feature of the mathematical landscape. The Big Bang isn't the moment when the universe was created from nothing. It's a boundary condition in a necessarily existing mathematical object. Asking what came before it is like asking what comes before the axioms of mathematics. The axioms don't come from anywhere. They're the starting point, the foundation from which everything else is derived. But I can hear your objection. Even if mathematical structures exist necessarily, that doesn't explain why we have this particular structure, this particular universe with these particular laws and constants. Why this equation and not some other equation? That's a fair question, and it brings us back to the multiverse idea. If all mathematically consistent structures exist, then we have all possible universes, and the question becomes not, why this universe, but why do I find myself observing this universe? And that has an anthropic answer, because this universe is one of the few capable of supporting observers like you. Think of it as a selection effect. Imagine there are a trillion different mathematical structures, each corresponding to a different possible universe with different laws of physics. Most of them are completely sterile, just dead mathematics with no interesting structure, no complexity, no life. But a tiny fraction of them have the right properties. They have stable particles, complex chemistry, energy gradients that allow for the emergence of self-replicating structures, evolution, and eventually consciousness. You can only exist in that tiny fraction of universes, so naturally, that's where you find yourself. It's not that this universe was selected for you. It's that you can only exist in universes that have certain properties, so those are the only universes you could ever observe. This is deeply unsatisfying to some people. It feels like a cop-out, like we're explaining the fine-tuning of our universe by saying there are lots of universes and we're in one that works. But it might actually be the most parsimonious explanation. It doesn't require a cosmic designer or a selection mechanism. It just requires that all mathematically possible universes exist, which might be the case if mathematical truth is necessary truth, and that observers can only emerge in universes with the right properties, which is trivially true. But let's explore another angle, one that takes us in a completely different direction. What if consciousness plays a role in the origin of the universe? Not in some mystical, woo-woo sense, but in a precise, physical sense grounded in quantum mechanics? You've heard of the measurement problem in quantum mechanics. Before a quantum system is measured, it exists in a superposition of all possible states. The electron is spinning both up and down. The particle is in multiple locations simultaneously. But when you measure it, when you interact with it in a way that leaves a record, the superposition collapses into one definite state. The electron is now spinning up, not down. The particle is here, not there. The act of measurement seems to play a crucial role in determining what's real. Now, most physicists will tell you that measurement doesn't require consciousness. Any interaction that creates a record, any decoherence event where the quantum system becomes entangled with its environment, counts as a measurement. A photon hitting a detector, a particle colliding with another particle, these things cause the wave function to collapse, or, in the many-worlds interpretation, cause the universe to split into branches. Consciousness isn't special. It's just one particular type of physical process among many. But a minority view, championed by some physicists and philosophers, suggests that consciousness might indeed be special. That the collapse of the wave function isn't caused by decoherence or environmental interaction, but by conscious observation. That reality doesn't become definite until a conscious mind observes it. This is called the consciousness causes collapse interpretation, and while it's not mainstream, it's not pseudoscience either. It's a serious interpretation of quantum mechanics with some interesting implications. If this view is correct, if consciousness plays a role in actualizing reality from quantum possibility, then the origin of the universe becomes deeply entangled with the origin of consciousness. Before consciousness, there was only potentiality, quantum superpositions of all possible states, a universe that existed in all possible configurations simultaneously. The Big Bang wasn't a single definite event. It was a superposition of all possible Big Bangs. Only with the emergence of consciousness, whether that happened on Earth with humans, or elsewhere in the universe with other beings, or perhaps with some form of proto-consciousness inherent in matter itself, did one particular history become actualized. This leads to a paradox. How can consciousness actualize the universe if consciousness is a product of the universe? If the Big Bang didn't become definite until consciousness observed it, but consciousness couldn't exist until billions of years after the Big Bang, then what's going on? The answer might involve retrocausality, the idea that effects can precede their causes at the quantum level. Your observation of the cosmic microwave background today might be what actualizes the Big Bang 13.8 billion years ago. The wave function of the entire universe might remain in superposition until conscious observers emerge and collapse it retroactively. This sounds insane, but it's not entirely without precedent. Quantum mechanics already includes phenomena that seem to involve backward causation or at least correlation across time that defies our intuitive notions of cause and effect. The delayed choice quantum eraser experiment shows that decisions made in the present can affect the behavior of particles in the past, at least from a certain interpretive standpoint. If the universe is fundamentally quantum mechanical all the way down, then the same weird temporal dynamics might apply to cosmology. John Wheeler, one of the great physicists of the 20th century, proposed something called the participatory anthropic principle. The idea is that conscious observers aren't just passive recipients of a pre-existing reality. They're participants in bringing that reality into being. The universe needs observers to become actual, and observers need the universe to come into being. It's a self-referential loop where the universe and consciousness co-create each other across time. This might sound like it belongs more in a philosophy seminar than a physics lecture, and you'd be right to be skeptical. Most physicists don't accept this view. They favor interpretations of quantum mechanics that don't give consciousness a special role. Either decoherence-based interpretations where environmental interaction causes collapse, or many-worlds interpretations where there is no collapse at all and all possibilities exist in a vast multiverse of quantum branches. But the consciousness causes collapse interpretation remains on the table, and it offers a provocative answer to the question of what came before space, before consciousness actualized it. The universe existed only as quantum potentiality, a superposition of all possible configurations, including configurations that don't even have space as we understand it. Let me take you somewhere even stranger. There's a concept in physics called the holographic principle, and it might fundamentally change how we think about the nature of space and the question of what came before it. The holographic principle suggests that all the information contained in a volume of space can be encoded on the boundary of that space, on a surface with one fewer dimension. Just like a hologram on a flat piece of film can contain all the information needed to reconstruct a three-dimensional image, the universe might be similar. Everything that happens in three-dimensional space might be encoded on a two-dimensional surface, and the three-dimensional space we experience might be a kind of projection or emergent phenomenon. This idea comes from studying black holes. Stephen Hawking and Jacob Bekenstein showed that the entropy of a black hole, the amount of information it contains, is proportional to the area of its event horizon, not its volume. That's weird. You'd expect that if you double the radius of a black hole, its information content would go up by a factor of 8 because volume scales with the cube of radius. But it only goes up by a factor of 4 because surface area scales with the square of radius. The information is somehow stored on the surface, not in the volume. Gerard, T. Hooft, and Leonard Susskind took this idea and ran with it, proposing that the holographic principle applies not just to black holes but to the universe as a whole. Everything in our three-dimensional universe might be encoded on a distant two-dimensional surface, perhaps at the edge of the observable universe or at the cosmological horizon. We think we're moving through three-dimensional space, but we might actually be patterns on a two-dimensional surface, and the third dimension is an illusion, an emergent property of the way information is organized on that surface. If this is true, and it's supported by some results in string theory, particularly the ADS/CFT correspondence, then space itself is not fundamental. It's emergent. It arises from the organization of information on a lower dimensional substrate. And if space is emergent, then asking what came before space might be like asking what came before temperature. Temperature is an emergent property of the collective motion of particles. Individual particles don't have temperature. Only groups of particles in aggregate have temperature. At the level of individual particles, the concept doesn't apply. Similarly, space might only exist at a certain scale when information is organized in a certain way. At a more fundamental level, there might be no space, just information or quantum bits or something even more abstract. Before the Big Bang, there might not have been space because the information hadn't organized itself in the right way yet. There was the substrate, the lower dimensional surface, or the quantum information, or the fundamental degrees of freedom, but not space as we experience it. Space crystallized out of this substrate when conditions were right, just like ice crystallizes out of water when the temperature drops. And just as asking what came before ice is answered by pointing to water, asking what came before space might be answered by pointing to whatever the fundamental substrate is, quantum information, or holographic degrees of freedom, or something else. This brings us to a deep and somewhat disturbing realization. Space might not be what you think it is. You experience space as this container, this empty stage on which matter and energy perform. It feels like the most real, most fundamental thing there is. But modern physics increasingly suggests that space is a derived concept, an approximate description that works at large scales but breaks down at the Planck scale, the smallest possible scale where quantum gravitational effects become important. At that scale, 10 to the minus 35 meters, far smaller than any particle we've ever detected, the smooth fabric of space-time predicted by general relativity gives way to something else. Quantum foam, or spin networks, or holographic bits, or something we don't have a name for yet. And if space is emergent, if it's not fundamental, then the question, what came before space, transforms into what is the fundamental substrate from which space emerges, and what were the conditions of that substrate before it had organized itself into what we call space. That's a very different question. It's not asking about temporal priority anymore. It's asking about ontological priority. What's more fundamental in the hierarchy of reality? The answer might be something like quantum entanglement. Some physicists, like Mark van Ramsdonk and others working on the connections between quantum information theory and gravity, have shown that the geometry of space might emerge from the entanglement structure of quantum fields. When quantum fields are highly entangled, they create the appearance of a connected space. When they're not entangled, space fragments or ceases to exist. Space is held together by quantum entanglement, and the geometry of space, which regions are close together, which are far apart, depends on the pattern of entanglement between different regions of the quantum field. If this is right, then before space, there was quantum entanglement. There were quantum degrees of freedom, whatever those are at the most fundamental level, perhaps strings or loops or branes or something even more abstract. And these degrees of freedom could be entangled or not. When they became entangled in the right way, space emerged. The Big Bang might have been the moment when the entanglement structure transitioned from some configuration that doesn't correspond to space as we know it into a configuration that does. Before that transition, there was something, these quantum degrees of freedom, but they weren't organized in a way that creates space. After the transition, they were, and space came into being. This is speculative, at the cutting edge of theoretical physics, but it points toward a possible resolution of the question. What came before space? Quantum information. Quantum entanglement. The fundamental degrees of freedom of whatever theory finally unifies quantum mechanics and general relativity, string theory, loop quantum gravity, or some other framework we haven't discovered yet. These things existed before space, and space emerged from them when the conditions were right. But even this doesn't fully answer the question, because now we're just asking what came before quantum entanglement, or before quantum degrees of freedom. And we're back to the same problem. Every answer generates a new question. Every layer of explanation reveals another layer beneath it. It's turtles all the way down, except the turtles keep changing what they're made of. Maybe that's the point. Maybe there is no final answer, no ultimate layer where we can stop and say, this is where it all comes from. Maybe reality is infinitely deep, with each layer emerging from another layer below it, and the quest for the ultimate ground of being is a quest without end. Or maybe there's a different kind of answer, one that doesn't fit into the usual framework of things causing other things or things emerging from other things. Let me introduce you to one more idea, perhaps the most abstract and difficult one yet. It comes from philosophy, but it connects to physics in interesting ways. It's the idea of a necessary being, something that exists not because something else caused it to exist, but because it would be incoherent for it not to exist. Something whose non-existence is impossible, not in a practical sense, but in a logical sense. You're familiar with necessary truths, statements that are true in all possible worlds. 2 plus 2 equals 4 is a necessary truth. There's no possible world where 2 plus 2 equals 5, assuming we're using the standard meanings of those words and symbols. All bachelors are unmarried is a necessary truth, true by definition. These truths don't exist because something caused them to be true. They're just true, necessarily, always. Could the universe, or the fundamental substrate of reality, be a necessary being in the same way? Could it be something that must exist, not because something brought it into existence, but because its non-existence is incoherent? This is what some philosophers call an ontologically necessary entity, as opposed to a causally necessary entity. A causally necessary entity is something that must exist because something else caused it. An ontologically necessary entity is something that must exist simply because that's its nature. This concept has traditionally been associated with theological arguments for the existence of God, a necessary being whose existence explains the existence of everything else. But you could potentially apply the same logic to the universe itself or to the fundamental physical substrate. Maybe the quantum vacuum, or the multiverse, or the mathematical structure underlying reality is ontologically necessary. Maybe it exists because it would be incoherent for it not to exist. Maybe non-existence isn't an option. If that's true, then the question, what came before space, dissolves. Space, or the substrate from which space emerges, exists necessarily. It doesn't need a cause. It doesn't need something before it. It exists because existence is its nature, and there's no possible world where it doesn't exist. The apparent contingency of the universe, the sense that it might not have existed, that something brought it into being, is an illusion, a result of thinking about the universe as if it were an object in the world rather than the totality of what exists. This is deeply philosophical, and it's not the kind of thing you can prove or disprove with an experiment. But it's a coherent position, and it offers a potential endpoint to the infinite regress of causes. If reality at its deepest level is ontologically necessary, then the regress stops. Not because we've reached a first cause, but because we've reached something that doesn't need a cause. But how do you determine what's ontologically necessary? How do you know whether the universe or the quantum vacuum or mathematical structures exist necessarily rather than contingently? This is where things get murky. Some philosophers argue that you can determine necessity through pure reason, through logical analysis of concepts. Others argue that necessity is a property that can only be discovered empirically by investigating the world. And still others argue that the concept of ontological necessity is confused, that it doesn't actually pick out a real property of things. I don't have an answer to this. I'm not sure anyone does. But it points to a fascinating possibility, that the question, what came before space, might not be answerable through physics alone. It might require input from philosophy, from mathematics, from logic, from fields that deal with the most fundamental questions about existence and necessity and possibility. Physics can tell us how the universe behaves, what laws govern it, how it evolved from the Big Bang to the present. But the question of why there's a universe at all, what grounds its existence, what came before it if anything did, these might be questions that transcend physics, that require a different kind of thinking. Let me bring this back to something more concrete, something we might actually be able to test in the not-too-distant future. One of the most exciting prospects in cosmology is the possibility of detecting primordial gravitational waves, ripples in space-time that were generated in the first fraction of a second after the Big Bang, perhaps during a period called cosmic inflation. These gravitational waves would carry information from the earliest moments of the universe, from times when the universe was so hot and dense that no light could propagate, when everything was opaque. But gravitational waves can propagate through anything. They're distortions of space-time itself, and they would have been traveling through the universe since its first moments, gradually stretching as space expanded, until today they would appear as incredibly faint polarization patterns in the cosmic microwave background. If we can detect these primordial gravitational waves, they would tell us something profound about the very early universe. They would confirm that cosmic inflation happened, a period of exponential expansion in the first tiny fraction of a second after the Big Bang, when the universe grew from subatomic size to macroscopic size in an instant. And inflation, if it happened, would tell us something about the conditions that prevailed before or at the very beginning of the Big Bang, because inflation is driven by a quantum field called the inflaton field, and the properties of that field depend on the physics of the very early universe. Moreover, if we can measure the details of these gravitational waves, their amplitude, their spectrum, how they vary with angular scale, we can potentially distinguish between different models of inflation, different proposals for what happened at the very earliest times. Some models of inflation connect to ideas about quantum gravity, about extra dimensions, about the multiverse. The gravitational wave signal might give us empirical evidence for or against these speculative ideas. We haven't detected primordial gravitational waves yet. There have been false alarms. Remember the BICEP 2 result in 2014 that initially seemed to show detection, but turned out to be contaminated by dust in our own galaxy. But the search continues. Multiple experiments are looking for this signal, from space-based detectors to ground-based telescopes to balloon-borne instruments. The technology is improving. The sensitivity is increasing. Within the next decade or two, we might have an answer. And if we do detect primordial gravitational waves, if we confirm inflation and learn about the physics of the earliest moments, we'll be one step closer to answering the question of what came before space. Not all the way there. Inflation still leaves open the question of what triggered it. What set the initial conditions? What came before the inflating field started rolling down its potential? But it would be progress. Real, empirical progress on a question that once seemed purely philosophical. That's the beauty and the frustration of this question. It sits at the boundary between science and philosophy, between the empirically testable and the purely speculative. Every decade, science pushes the boundary a little further. Things that were once pure philosophy, the age of the universe, the expansion of space, the quantum nature of reality, have become empirical questions with experimental answers. Maybe the question of cosmic origins will follow the same trajectory. Maybe in 50 years or 100 years, we'll have data from gravitational wave detectors and particle accelerators and space-based observatories that will tell us definitively what happened at the Big Bang, what came before it if anything, what the fundamental substrate of reality is. Or maybe we won't. Maybe this question really is beyond the reach of empirical science, forever trapped in the realm of speculation and competing theories that can't be distinguished observationally. Maybe the conditions of the very early universe are so extreme, the energy so high, the scales so small, that we'll never be able to recreate them or observe them directly. Maybe we'll have to content ourselves with incomplete knowledge, with theories that are consistent with what we observe but can't be proven, with a plurality of possible answers that we can't choose between. That would be disappointing, but it wouldn't be shameful. The fact that we've come this far, that we've traced the history of the universe back to fractions of a second after the Big Bang, that we've developed mathematical frameworks sophisticated enough to even ask these questions coherently. That's a tremendous achievement. We're apes who evolved on a small planet orbiting an average star in an unremarkable galaxy, and we've figured out the age of the universe to within 1% accuracy. We've detected gravitational waves from colliding black holes billions of light years away. We've measured the cosmic microwave background and confirmed that the universe was once in an incredibly hot, dense state. We've done all this with instruments we built from sand and metal and glass, with brains that evolved to do something completely different. So even if we never get a complete answer to what came before space, even if that question remains forever at the edge of what's knowable, we should marvel at how far we've come. And we should keep pushing, keep asking, keep developing new theories and new experiments, because that's what humans do. We're not satisfied with ignorance. We demand explanations. We want to understand. And who knows? Maybe the answer is simpler than we think. Maybe there's an insight waiting to be discovered, an elegant mathematical structure, or a profound physical principle that will make everything click into place. Maybe some brilliant physicist working in obscurity right now is on the verge of a breakthrough that will transform our understanding of cosmic origins. Maybe the answer has been staring us in the face all along, hidden in the equations of quantum mechanics or general relativity, and we just needed the right perspective to see it. Or maybe the answer is more complex than we can imagine, requiring concepts and mathematical tools that won't be invented for centuries. Maybe we're like Isaac Newton trying to understand quantum mechanics, not just lacking the right theory, but lacking the entire conceptual framework needed to even formulate the right theory. Maybe the question, what came before space, is like asking a medieval peasant to explain semiconductor physics. The words are there, the question is grammatically well-formed, but the conceptual gap is too large to bridge with current understanding. I keep circling back to the same realization, we don't know. And that's okay. That's where science lives, at the boundary of knowledge and ignorance, in the tension between what we understand and what remains mysterious. The question, what came before space, is one of the great mysteries, perhaps the greatest mystery. It probes the ultimate origin of everything. It asks why there's something rather than nothing. It challenges our deepest intuitions about causation and time and existence. Every answer I've given you today, time began at the Big Bang. The universe is a quantum fluctuation. Space is emergent from entanglement. Reality is mathematical and exists necessarily. The universe is cyclic or eternal. Consciousness plays a role in actualizing reality. Every one of these is speculative to some degree. Some are more supported by evidence and mathematical consistency than others. Some are mainstream views held by many physicists. Others are fringe ideas championed by only a few. But none of them is proven. None of them is the final word. That's both humbling and exciting. Humbling because it reminds us how much we don't know, how small we are in the face of cosmic mysteries. Exciting because it means there's still so much to discover, so many possibilities to explore, so many potential breakthroughs waiting to be made. The question of cosmic origins is still open. The final chapter hasn't been written. We're living through the age of discovery, watching as humanity grapples with the deepest questions about existence. So what was before space? The honest answer is, we're working on it. We have ideas, theories, mathematical frameworks. We have observations that constrain the possibilities. We have experiments planned that might provide crucial data. But we don't have the final answer yet. And maybe that's exactly where we should be at this point in human history. Far enough along to ask the question meaningfully, to propose plausible answers, to design tests that might distinguish between them, but not so far along that the mystery is solved and the adventure is over. The universe is under no obligation to make sense to you. It doesn't care whether you find the answers satisfying or whether they conform to your intuitions. It simply is what it is, operating according to principles that might be beautiful or might be arbitrary, might be simple at the deepest level or might be irreducibly complex. Our job isn't to dictate what the answer should be based on what we find philosophically pleasing. Our job is to follow the evidence wherever it leads, to let nature tell us how reality works rather than imposing our preconceptions on it. And nature has been telling us some very strange things. It's been telling us that time is relative, that space can warp and stretch, that particles can exist in multiple states simultaneously, that the vacuum of space isn't empty, but seething with quantum activity. It's been telling us that our intuitions, forged in the everyday world of medium-sized objects moving at moderate speeds, don't apply at the extremes. It's been telling us that reality is far stranger, far more subtle, far more mathematically intricate than we ever imagined. So when we ask what came before space, we should be prepared for an answer that defies our intuitions, that challenges our assumptions, that requires us to think in new ways. We should be prepared for the possibility that the question itself is malformed, that it smuggles in assumptions about time and causation that don't apply. We should be prepared for multiple possible answers, a landscape of theoretical possibilities that might all be consistent with the limited data we have. And we should be prepared for the long haul, for the possibility that answering this question will take decades or centuries or might never be fully resolved. But we should also be hopeful, because history shows that humans are good at solving problems that seem impossible at first. We've cracked mysteries that seemed utterly intractable. We've developed technologies and theories that would seem like magic to our ancestors. We've pushed back the boundaries of ignorance again and again. There's no reason to think we've reached the limit of what's knowable. There's no reason to think that the question of cosmic origins is forever beyond our grasp. So we keep pushing. We build better telescopes and particle accelerators. We develop more sophisticated mathematical frameworks. We train new generations of physicists and cosmologists and philosophers to think deeply about these questions. We fund research into the foundations of physics, into quantum gravity and cosmology and the structure of space-time. We encourage wild speculation and careful observation in equal measure. We create an intellectual environment where radical new ideas can be proposed and tested. And maybe, just maybe, one day we'll have an answer. Not just a theory or a model, but a genuine understanding of what came before space, or why that question doesn't make sense, or what the deeper reality is from which space emerges. We'll look back at this era of confusion and multiple competing theories the way we now look back at pre-Copernican astronomy or pre-Darwinian biology, as a necessary stage in the development of human knowledge, a time when we knew enough to ask the right questions, but not enough to answer them definitively. Until that day comes, if it ever does, we live with uncertainty. We hold multiple possibilities in mind simultaneously. We distinguish carefully between what we know, what we think we know, and what we're just guessing at. We remain humble in the face of cosmic mysteries while simultaneously remaining confident in the power of human reason and observation to uncover truth. What came before space? I don't know. But I know we're asking the question in increasingly sophisticated ways. I know we're gathering data that constrains the possibilities. I know we're developing theories that might someday be tested. And I know that the search for the answer, the process of pushing against the boundaries of human knowledge, is itself worthwhile regardless of whether we ever reach a final conclusion. Because in the end, asking what came before space isn't just about satisfying curiosity. It's about understanding our place in the cosmos, about knowing where we came from in the deepest possible sense. It's about whether the universe is fundamentally intelligible, whether there are reasons for things to be the way they are, whether reality at its deepest level makes sense. These are questions that speak to something profound in the human spirit: the need to understand, the refusal to accept ignorance as the final answer, the conviction that the universe can be known. And so we keep asking. We keep searching. We keep thinking and observing and theorizing. We keep pushing against the darkness of ignorance with the light of knowledge. And if we're very lucky, if we're very clever, if the universe is kind enough to leave clues that we can decipher, maybe someday we'll know. Maybe someday someone will crack the code, solve the puzzle, answer the question that has haunted humans for as long as we've been able to contemplate our own existence. What came before space? The answer is out there, somewhere, hiding in the mathematics of quantum gravity or the data from gravitational wave detectors or the elegant structure of a theory we haven't discovered yet. Or maybe the answer is that the question is wrong, that we're asking about something that doesn't exist, like the color of jealousy or the sound of purple. Either way, the search continues. The mystery endures. And we keep asking, keep wondering, keep pushing toward understanding. Because that's what it means to be human. That's what it means to be conscious beings in a vast and mysterious universe. We ask questions. We seek answers. We refuse to accept that anything is truly unknowable. We demand explanations. We build theories. We test them. We refine them. We get closer and closer to truth, even if we never quite reach it, even if truth is always a little further away than we think. What came before space? Stay curious. Stay skeptical. Stay open to possibilities. And maybe, just maybe, you'll live to see the day when someone finally answers that question in a way that makes sense, that fits the evidence, that elegantly explains the origin of everything. Or maybe you won't. Maybe that day is centuries away or will never come. But the attempt to answer it, the intellectual journey toward understanding, the refinement of our concepts and theories and observations, that's valuable in itself. That's what makes us more than just biological machines replicating our genes. That's what elevates us to something greater, something that can contemplate the cosmos and ask why it exists. What came before space? I don't know, but I know it's worth asking. And I know that every generation that asks it gets a little bit closer to understanding, even if the understanding always seems to recede as fast as we approach it, even if each answer generates 10 new questions. That's the nature of deep knowledge. That's the nature of ultimate mysteries. And that's exactly as it should be.